In this video tutorial, I will describe the concept of projectile motion. We will look particularly at horizontal projectiles. The essential question for this unit is how do we describe the motion of an object moving in two dimensions simultaneously? The guiding questions are, how do we describe the changes in position, velocity, and acceleration for an object moving in two dimensions? And how do we use expressions to analyze the motion of projectiles? A projectile is an object that is launched into the air. For example, tennis balls, arrows, baseballs, bullets, students, and many more. In order to be considered a projectile, gravity must affect the motion. The path, or the trajectory of a projectile, is parabolic. It is shaped like a parabola. The path is shortened under the effects of air resistance. So you can see in the diagram, the blue path, the blue trajectory, is without air resistance, and the black path of the soccer ball is the trajectory with air resistance. The ball does not go as high, and it does not go as far. To create the parabolic trajectory, we need to first look at each dimension separately. We'll begin with the horizontal dimension. So we're going to imagine that we can turn gravity off and also turn air resistance off. And if a cannon shoots a cannonball and we shut gravity and air resistance off, then if it's given an initial horizontal velocity, that horizontal velocity will stay the same. And in the next instant, the ball will be here. And it will continue to move. And if you notice, because gravity is off and air resistance is off, the cannonball doesn't fall, but it also does not slow down. Therefore, the distance covered in each increment of time is equal. And you can see that in the diagram. So the distance traveled during each time interval is the same. The speed is constant, and the acceleration horizontally is 0. This results in the distance being equal for every increment of time. We can also take a look at the vertical dimension. And again, we have to look at the vertical dimension completely separate from the horizontal dimension. So we'll imagine we turn gravity on and keep air resistance off. Because we're only concerned with the vertical dimension, we do not take into account the initial horizontal velocity of the cannonball. We are only concerned with what's going on in the vertical dimension. So we assume that the cannonball starts with an initial vertical velocity of 0, and as time goes on, we can see that the cannonball falls toward the ground. Notice the distance covered in each increment of time is increasing. This is because the speed of the object is increasing. The acceleration is 9.8 meters per second squared in the vertical dimension. So that means for every second that passes, the object speeds up by 9.8 meters per second. This is essentially a case of free fall. It is important to note that the horizontal and vertical motions are completely independent of each other. This is where that concept of independence of vectors comes up again. Time links the horizontal and vertical motion because the time that the object has to fall is the time that the object is allowed to move forward with the initial horizontal velocity. Time links the two dimensions. When we put both the horizontal motion and the vertical motion together, we see that the cannonball, or the projectile, undergoes a trajectory that looks like a half parabola. We can label certain parts like the initial height or the maximum height, And we can also label the horizontal distance from the base of the cliff, or how far the projectile goes from its starting point, which is called the range. We can also look at the vectors separately. For an object that is undergoing horizontal projectile motion, we can take a look at the horizontal velocity separate from the vertical velocity. As we said before, the horizontal velocity is constant. The object doesn't speed up or slow down. We're assuming that air resistance is negligible. So, the initial velocity that the cannon provides to the cannonball is velocity horizontally throughout the whole trip. But the vertical velocity is increasing under the influence of gravity. So if we were to illustrate the velocity vector for the vertical velocity, we would see the vertical velocity is increasing. If we put these vectors head to tail, we can create the resultant velocity, which we see is increasing in magnitude, but also is changing in direction. For an object that is undergoing projectile motion, the only force acting on it is gravity. Therefore, that is the only force that's creating an acceleration. So, because there's no forward or backward force, there's no air resistance, there's no wind, the horizontal acceleration is zero. So if we were going to draw in acceleration vectors, there are no horizontal accelerations. However, if we look at the vertical acceleration is provided by gravity, which causes objects to accelerate at the rate of 9.8 meters per second squared throughout the entire trip. So the acceleration remains the same throughout the entire path and is a value of 9.8 meters per second squared. You may wonder how the time of flight is different for an object that is dropped and one that is launched with an initial horizontal velocity. Time of flight is a vertical phenomenon, meaning that it depends on the initial height of the object only. If we view the position of a projectile that is dropped compared to a projectile with an initial horizontal velocity, we see that the vertical positions line up. So what this means is that an object that is launched horizontally will take the same amount of time to hit the ground as an object that is dropped from the same height. This is because the horizontal motion is completely independent of the vertical motion. So although, with respect to the horizontal dimension, one is moving and the other is not, with respect to the vertical dimension, both are essentially in free fall, with an acceleration of 9.8 meters per second squared. An object given a faster initial velocity will have a larger range, but only travels further because of a larger horizontal velocity, not because of a larger time of flight. The red projectile and white projectile will spend the same amount of time in the air. You should also note that the mass of the projectile does not influence the time of flight either. All objects, regardless of mass, will fall at the same rate. And now we can also say all objects, regardless of their initial horizontal velocity, will fall at the same rate. Let's take a look at a practice problem. A mouse runs off a ledge that is 2 meters high with an initial horizontal velocity of 3 meters per second. We'll assume that the mouse is running off the ledge and landing onto a trampoline. How long does it take the mouse to reach the trampoline below? How far from the base of the ledge must the center of the trampoline be placed so the mouse lands in the center? And what is the mouse's resultant velocity just before striking the trampoline? Pause the video for time to work on the solution. To solve the problem, we have to analyze each dimension separately. So we will create a T-chart to separate our horizontal and vertical information. In the horizontal dimension, we know the initial velocity of the mouse is 3 meters per second. We also know that because there are no forces acting horizontally, such as wind or air resistance, the horizontal acceleration is 0. There is no other information given or implied about the horizontal dimension. Because that's not enough information to solve the problem, we have to look at the vertical dimension. The mouse is running off the table with an initial horizontal velocity of 3 meters per second. Since it only has an initial horizontal velocity, the initial vertical velocity is 0. In the vertical dimension, the mouse is essentially in free fall with an initial velocity, VIY, of 0. The acceleration in the vertical dimension is 9.8 meters per second squared, as always. We call the acceleration positive because the mouse is gaining speed on the way down. Finally, we know the distance the mouse falls vertically is 2 meters. Based on the information given and implied for the vertical dimension, we can solve for the time in the air. The formula that has the variables we need is the distance formula. I'm going to replace distance, d, with delta y, or the displacement in the y dimension. This is equal to VIYT plus 1/2 AYT squared, where VIY is the initial velocity in the y dimension, and AY is the acceleration in the y dimension. Plugging in the initial velocity in the y of 0, we can get rid of the first term. We plug in 2 meters for our displacement, and then 9.8 meters per second squared for our acceleration in the y. And rearranging, we can solve for t, and we find the time to be 0.64 seconds. For part B, we are looking for the range, or how far from the base of the loop the mouse lands. Since this is horizontal information, we have to use the distance formula, where I'll call the distance delta x, which is equal to VI in the x times t plus 1/2 A in the x times t squared. The acceleration in the x dimension, or horizontally, is 0, so the second term is now gone. Plug in 3 meters per second for the horizontal velocity, and the time is from the vertical dimension, 0.64 seconds. The time that the mouse is allowed to move forward with the speed of 3 meters per second is the time that it takes the mouse to fall. So time links the two dimensions, and it can be used in either horizontal or vertical dimension. Solving for the displacement, we find that the mouse lands 1.92 meters away from the base of the ledge, so this is where the trampoline should be placed. Part C asks us to find the resultant velocity. Resultant velocity includes magnitude and direction. Because the projectile travels in 2 dimensions, we have to find the horizontal speed, then the vertical speed, and then calculate their resultant. In the horizontal dimension, the initial velocity is 3 meters per second, and the acceleration is 0. This means that the projectile, the mouse, is traveling at a constant speed in the horizontal dimension. So the horizontal speed at all points in the mouse's motion will be 3 meters per second, including just before it strikes the ground. However, in the vertical dimension, the mouse's speed is increasing from 0 at the rate of 9.8 meters per second. We know the mouse falls for 0.64 seconds, so if we use the acceleration equation and rearrange it to solve for final velocity, in this way it looks like Vf equals Vi plus At. V initial is 0. We can plug in the acceleration of 9.8 meters per second squared and the time that it falls, 0.64 seconds, and we find the vertical velocity just before it strikes the ground to be 6.3 per second downward. Because these velocity vectors are perpendicular to each other, we can create a head-to-tail sketch and determine the magnitude and direction of the resultant using Pythagorean theorem and trig. So we place a vector horizontally, and that's the 3 meters per second. And then the mouse is also traveling downward with a velocity of 6.3 meters per second. We place these head to tail and find the resultant using Pythagorean theorem and trig. We find the answer to be 6.98 meters per second at 65 degrees below the positive x-axis. Let's try a second problem. An airplane pilot, flying at 600 meters above the ground, wants to drop a care package at point C, which is 137 meters away. How fast does the airplane have to be flying so that the package lands exactly at point C? One thing that we should note in this problem is that because the package is being dropped by the plane, the package has the same horizontal velocity as the plane when it's released, and the vertical velocity would be 0. Pause the video for time to work on the solution. So let's check our work. We again separate our information into horizontal and vertical dimensions. The range of the package must be 137 meters if it is to strike point C. The horizontal acceleration is 0, and we are looking for the initial horizontal velocity, or the velocity of the plane. In the vertical dimension, the initial is 0, the acceleration 9.8 meters per second, which is positive because it's speeding up, and the height from which the package falls is 600 meters. We can find time of flight from the vertical dimension using the distance formula. And again, the initial is 0, so the first term cancels. Plugging in our information in the vertical dimension, we find the time to be 11.1 seconds. Plugging that time into the horizontal dimension, because it links the two dimensions, we use the distance formula. The acceleration is 0 in the horizontal, so the second term is gone. We plug in the distance and the time and find the velocity horizontally to be 12.3 meters per second. Let's try one last practice problem. People in movies often jump from buildings into pools. If a person jumps horizontally by running straight off a rooftop from a height of 30 meters to a pool that is 5 meters from the building, with what initial velocity or speed must the person jump? Pause the video for time to work on the solution. We will separate our information into horizontal and vertical. We do not know the initial velocity. The acceleration horizontally is 0, and the distance, or the range, is 5 meters to the pool. In the vertical dimension, the initial velocity is 0, acceleration is 9.8 meters per second squared, and the height from which he is jumping is 30 meters. So we need to find time from the vertical dimension, because we don't have enough information in the horizontal yet. So using the displacement formula, or the distance formula, we find the time to be 2.5 seconds in the air. We can then use that time in the horizontal dimension to figure out the initial velocity. Plugging in our information and solving for v initial in the x, we find the velocity to be 2 meters per second. In addition to calculating unknowns, such as range, height, time of flight, and final velocity, you may have to use expressions for positions as a function of time to analyze the motion of a projectile. For example, in the horizontal dimension, position is described by the distance formula. But the acceleration is 0, so the second term is 0. Therefore, the expression for horizontal position as a function of time is delta x equals vi times t, where vi is the value of the initial horizontal velocity. You may be given an expression for position as a function of time, like this one, which says delta x equals 4t. If you compare this expression to the one above it, the distance formula, you can see that the initial horizontal velocity is considered 4 meters per second, and the acceleration is 0 meters per second squared. When given an expression like the one shown, you may be asked for the values of acceleration and velocity, and you can determine those by relating that expression to the distance formula. In the vertical dimension, position can also be described by the distance formula, where vi is 0, so the first term is 0. Therefore, the expression for vertical position as a function of time is delta y equals 1/2 at squared, where a is the vertical acceleration. You may be given an expression for position as a function of time like this one, which says delta y equals 1/2 10t squared. If you compare this expression to the one above it, you can see that the initial vertical velocity is 0, and the acceleration is 10 meters per second squared. However, it may not be as simple. You may also be given an expression like this one, delta y equals 5t squared. Comparing that to the equation above, we have to realize that 1/2 a, or 1/2 the acceleration, equals 5. So then the acceleration actually equals 10 meters per second squared. Important to remember the 1/2 in the equation. So again, we can see from either of these vertical displacement expressions that the acceleration in the y is 10 meters per second squared, and the v initial in the y is 0. From this video, we can draw a few conclusions about projectile motion. First, projectile motion is parabolic. For now, we're looking at problems that are taking a look at the second half of parabola. Projectile motion is also motion of objects that are under the influence of gravity only. For all of our cases, we neglected air resistance, wind, and any kinds of friction. It is also important to notice that horizontal and vertical motions are independent of each other and must be treated as such. And this is why in the vectors unit we had the conversation about independence of vectors. Making one vector larger in one dimension does not affect the other dimension. However, the resultant will be affected. Horizontal velocity doesn't change because horizontal acceleration is 0. We saw that for sure in these problems. The horizontal acceleration is always going to be 0 as long as we neglect air resistance and friction. Vertical velocity will always increase in these horizontal projectiles because the vertical acceleration is 9.8 meters per second squared. Time links the two dimensions. We can solve usually for time in the vertical dimension because it is a vertical phenomenon, and then we can use that time in the horizontal dimension to find any other missing pieces. Time is common for the two dimensions, even though each dimension is independent of the other. And finally, projectiles that are dropped from a height have the same time of flight as projectiles that are launched with an initial horizontal velocity from the same height. As long as the heights are the same, the time of flight is the same, regardless of the horizontal velocity.